Good afternoon, everyone. So it's my pleasure to give this seminar just to share some maybe progress in our program as well as in my research group. So Case Western is happy to be a partner, be a part of the national UTC that focuses on transportation infrastructure durability and life extension. WSU is a leader on this effort. So because the name of Case Western might sound unfamiliar to a lot of people, but we are a university located in Cleveland, Ohio. So this actually is a photo, shows the city downtown, essential center of the city, Cleveland. It's a very beautiful place. That's right beside Lake Erie. And then our campus is about like 3 or 4 miles away from downtown. It's a very pretty campus. And we have very good students that essentially hold up the spirits of Case Western. Department-wise, Case has been known for a technology in the deep foundation industry called the Case method. So over the years, our faculty members and students have been trying to develop like leading edge research. We also build a lot of infrastructures like this large-scale structure testing facility that features like a strong wall and a strong floor, allow to run large-scale structural testing. So definitely our colleagues will look forward to opportunities to collaborate with like whether partners within the center or maybe other partners. We also have an array of shaking tables that's allowed to study the issues such as seismic response that's considering the phase lag in the wave propagation, for example, which is the case for pipelines or multi-span bridges. We also have unique facility, geotechnical centrifuge, that's allowed to use a scaled model to ramp up the behaviors of a large-scale structure. In the recent years, we built a lot of like new additional facilities, like the geotech engineering research and teaching laboratories. And we are in the process to build a new concrete laboratory for research and education purpose. So I think we look forward to a lot of opportunities to work with our partners within the center and beyond the center. So that's the overview for our department and for myself. So I had a training primarily in civil engineering, but also took a lot of interdisciplinary training in electrical engineering, computer science domain. So like my research in many cases lies in the interdisciplinary domain. So roughly the research areas in my group, so we focus a lot about sensing technologies, a lot about materials, all kinds of porous material, geomaterials, from computation modeling, multi-scale behaviors, and also from a system aspect, from data system-driven engineering issues. So one thing maybe try to see, like essentially continue to recruit highly motivated students. Like this is my contact information. If you know, or you are a student, or if you know of a student who are looking for maybe a challenging and rewarding like a research like training in the PhD stage, please have them to contact me. So for today, like I'll try to give an overview about our research in terms of like sensing and NDT domain, with focus on a technology based on electromagnetic wave. So I will first give a technical background and then discuss about a few different type of applications based on this sensing principle. So like time domain reflectometry, I think for people in the transportation, like a pavement industry, you may heard about this terminology, acronym as TDR. So essentially it's a radar technology that we launch like a fast rising electromagnetic pulse, electrical pulse that's transported through what's called coaxial cable waveguide to a measurement probe. So whatever the difference in the material properties or change in the interface would cause reflections in the electromagnetic wave response, like a schematic showing here. So essentially, it provides a way to long-disruptive like sense a material behavior or like structural interface behaviors. So this technology was like originally utilized by electrical engineering to detect breaks in cables. In civil engineering, since 1990s, there has been seen a lot of potential applications for civil engineering materials or civil infrastructure, health monitoring purpose. So this is one schematic concept. For example, using what's called TDR principle, or this like a pass echo method, like bat used to detect prey. So essentially, with pre-installed monitoring probe for the along slope, the sliding deformation of landslides would then shear off the slope, cause a structural interface change, and then the propagating electromagnetic wave then it generates response. That's with the extent of response decided by the extent of the interface development, because the shearing of the monitoring probe or cable. That's then allowed to monitor the extent of landslides. So this is just one of the example to utilize the behavior of guided electromagnetic wave to detect the structural discontinuity. There's a lot of like a response also to the material that allow the technology to be utilized for material sensing purpose. So the basic principle is like we send out the like fast rising electrical pulse, which is like typically in the picosecond range. It's very fast. And then when they encounter the change in the interface or encounter the change in the materials, then they generate reflection. So for this case, the first reflection corresponds to the electromagnetic wave enters into the material, and then the other reflection generates when the electromagnetic wave reaches the end of the waveguide. So essentially, these two reflections then allow to determine how fast the electromagnetic wave travels inside the material, and then that is related to a property, electrical property of a material called dielectric constant, or in the TDR domain, it's also called apparent dielectric constant, because dielectric constant tends to be frequency dependent. Well, this one gave a bulk equivalent value, represented overall behavior of the material in terms of dielectric response. And then in the other domain, like when the electrical signal travels inside the material, the energy got attenuation, and so that's related to how conductive the material is. It's called electrical conductivity, which can be obtained from the retained energy from the signal response. So because with this sensing principle, it can be utilized to detect the interface, like landslide monitoring purpose, or detect like monitoring the material behaviors, primarily based on a change in the electrical properties of the material, including dielectric constant and electrical conductivity. So for a lot of civil engineering materials, mostly particularly like soil, asphalt, concrete. These are what called rock. They are porous materials. So which means they are included for multiple phases, with air phase, water, solids most commonly. Then the one unique behavior in terms of electrical properties is water has a very large dielectric constant because of the polar molecules in the water. So typically has a dielectric constant that's about 81 in theory. Well, compared like for the air and the solid phase, the values are pretty small, much smaller. So overall, it makes the overall dielectric constant of the mixture to be very dependent upon the amount of moisture inside the material. So this essentially gave it a way to, from the measure overall like a bulk dielectric constant, is very strongly related to the amount of moisture condition in regular civil engineering material. So based on this observation, there's some studies primarily in the water resource community, agriculture. So they found this relationship between the measured dielectric constant by the electromagnetic wave, like TDR, is universally related to what's called a volumetric water content. That serves the purpose for irrigation, this kind of purpose. And then So what we have been doing is like extend this like a monitoring principle for civil infrastructure purpose. So the first domain application I try to describe is for construction quality control. So we know like the earthwork compaction, like soil compaction is typically the most common procedure in civil engineering construction. We typically lay down soil in layers and with a given thickness, and then try to use specific adaptive compaction equipment based on type of soil to do the effective compaction with the goal to improve the strength, reduce the settlement, improve the modulus. So based on this amount of energy we apply, so we mechanically stabilize the soil that will serve as the strong support for the other infrastructure, such as pavement or other type of structures. And then in that, for the quality control, like moisture density measurement is the primary way for institutes construction quality control for this purpose. And then in the practice side, we have a lot of like a standard method for this, for measure, for example, soil, water content, density for construction decisions. There's like a range from the procedures that may be time consuming. For example, we maybe sample the soil to the lab, to the oven, to put in the oven to dry out the soil to measure water content. Sometimes maybe use microwave oven to accelerate the drying process. There's also like a chemical based way using its strong moisture absorption material to absorb the moisture away from the soil. So these also common technologies. Now the standard practice in the field is what's called the nuclear method, which using like a neutron thermalization process to measure the amount of moisture. And then for the density aspect, like there are also like procedures like sand cone, rubber balloon. Both are like an intrusive technology. Involve a lot of labor to dig holes into the soil to make measurement. And then there's like a technology like a driving cylinder, which is only applicable for cohesive soils. So in terms like the current standard practice in the construction industry, like the nuclear method is essentially gold standard. So nuclear method is based on the principle using like two different type of radioactive source. One is the neutron source. The neutron has a like a atomic weight similar as the hydrogen. So when the fast neutron is released by neutron probe, it collide into the hydrogen, and the energy was passed on to hydrogen, and then gradually, because the hydrogen is constrained by oxygen in a water molecule, so essentially gradually the energy dampened away because of the intermolecular vibration, because the hydrogen cannot be released by the oxygen because of the strong like a chemical bond. So essentially the detector, like essentially because of that, the hydrogen then cannot reach the detector to be detected if there's water inside of the soil, primarily if there's hydrogen inside the soil. So that's then based on the amount of hydrogen like that detector can detect, then we can infer what's the density of hydrogen inside the soil, or and based on the relationship between hydrogen and water, then we can find out the amount of water. So essentially, that's that's provide a way for water content measurement. For the density, mostly it's the nuclear gauge or the nuclear method using gamma ray attenuation, because gamma ray is a very features very high penetration power. So the amount of penetration is only decided by density of a material. So essentially, with a gamma ray source released, the amount of the gamma ray detected by the detector is only decided by the density of the material, while the gamma ray propagate. So because of these two different individual sensing principle, it provides individual measurement of water content and the density, allow to institute quick construction quality control. In operation wise, these are also the operational time typically ranges between 3 to 5 minutes. Depends upon the operation procedure that involves drilling a hole or not. So it's very quick in the field practice. But then there's also limitations, because the use of a radioactive source has potentially safety concern. Also, they are subject to very strict regulatory requirement by from the like safety professional safety standard point. So what we have worked on was to develop like technologies that may provide a quick way to manage the water content density for quantity control purpose, but in the same time, they're safe to use. So technology will, like we use the TDR, like electromagnetic wave principle TDR for this purpose. So that the schematic concept involves we installed these mechanical probes into the soil that serve as a waveguide for electromagnetic wave, and then we then launch the electric signal that propagate to the soil. And then at the interface, when the signal enters into soil, we generate a reflection. And then at the end of the probe, it generates another reflection. And then interestingly, based on what we discussed, essentially like the extent of the physical property in soil, like water content density, why it's very related to what's called dielectric constant, apparent dielectric constant as it described in the technology principle. So for soil at a constant dry density with increasing water content, the dielectric constant continue to increase in a systematic way. Similarly, electric conductivity increase in a change in the systematic way. Similarly, at the similar water content, different density, we have seen similar of the, like a trend of variation. So essentially, from a TDR measurement, we have two independent pieces of information: dielectric constant, electric conductivity, and we have two unknown information, which is water content, density of soil. And then by developing this calibration, and then we then provide, like essentially we have two equations to solve for two unknowns. So we then directly measure the water content density. So that's the basic principle. Based on this concept, we then develop these tools like this one, involve you use a template drive the waveguide into the space, into the ground, and then we then put the waveguide as a transformer to launch the wave into the signal, electrical signal, into the ground, and then make measurement. That's one additional procedure in the original testing method. One involves the sample soil to validate with another measurement. In the refined procedure, we come up with is we only needed one step, what's called one-step method, which is incorporated with ASTM standard 6780. So essentially, drive the rod into the ground in a spatial pattern that emulates a coaxial cable, and then we launch the signal into the ground, and then get the water content density, and then we then get the dielectric content and electric conductivity. From that, we get water content density right away. So this is something like the field tool we developed from this study. Essentially, it's a very portable equipment with handling very similar to nuclear gauge in terms of size to carry around, and then drive the rod into the ground and then make measurements. And then actually we did a study at the Indiana DOT testing site with side-by-side comparison with nuclear gauge, and then the results is pretty consistent. And in most locations, we actually achieve even higher accuracy compared with oven-dried measurement. And then we did a lot of study, like validated on different types of soil. So in terms of, right now, there's in the construction industry, people are moving to what's called intelligent compaction, which means we don't want to just measure measurement at a few locations. We want to measure the full field of the construction site. So essentially, like for the intelligent compaction, mostly it's based on stiffness measurement, based on the amplitude of vibration. If the ground is compact, well compacted, then we have more like a high frequency, low amplitude vibration. So based on these kind of instruments, we then institute construction quality control into the intelligent compaction technology. But then for implement this one, the moisture still play a critical role, because with the same size condition, just changing we just change the moisture condition by waiting wait for some time, the stiffness will change significantly. So essentially, measure the stiffness alone is not insufficient for the intelligent compaction technology. So that this one still requires moisture content measurement, which with like electromagnetic wave like TDR provide a potential wave. Actually, we developed this. We developed this like a flat belt type of sensing mechanism that allowed real-time monitor the moisture distribution associated with intelligent compaction process. So that's for the quantity control for soil, and then maybe I can discuss about the quantity control for concrete. So we investigated into how do we use TDR technology for early stage concrete instrumentation. So the principle is pretty illustrative because keep in mind that TDR is very sensitive to the amount of moisture. And we saw like in the concrete design, the water is an important parameter. The water content, the water cement ratio are the key design among the key design parameters for concrete. So like essentially the dielectric constants will give the information about the amount of water in concrete and allow to link that one to water cement ratio. And then electric conductivity, which is related to extent of hydration, because from the fresh concrete, which is in the liquid status, we can imagine the electric conductivity can be pretty high. With concrete hydrates become solid format, the electric conductivity will be lower. So essentially they have a link. And then similarly, the hydration process in concrete consumed water, consumed amount of water. So that's then be reflected in the dielectric constant, which then determine how fast the electromagnetic wave propagate in concrete. Then that allows to estimate the extent hydration. And the electric conductivity, which reflect the arrangement status of material inside the concrete matrix, is linked to setting time. So that's conceptually, there's a lot of link from electromagnetic response of a material to the behaviors that observes inside concrete hydration process. So with this in mind, then we look into like developing these monitoring sensors, monitoring probes. That's to see if how the like concrete materials would respond in terms of the changing of that electromagnetic properties. So these are the like a very like inexpensive probes we use for monitoring purpose. So like with TDR, which is a electric technology, so we can everything for monitoring process can be automated. So like to illustrate the basic observation, for example, with a fresh prepared concrete, we see relative large time delay, which corresponds to larger dielectric constant, which also related to the large amount of water. And then we see less about energy return in the long signal. So that's related to how electric like higher electric conductivity. With hydration curing time evolves, we see less amount moisture. So that leads to a smaller dielectric constant and lower electric conductivity. So that's demonstrates a very systematic response of the electromagnetic property of the material when it's subject to hydration process in concrete. So if we put the electric like conductivity with time, then we clearly see the transition. There's a clear transition stage in the electric conductivity inside in the hydrating concrete. So that's allowed to determine, for example, indication of the initial setting because of the geometry arrangement, and then there's a final setting because of different mechanism controlling chemical hydration. That may be diffusion control versus the other control mechanism. So with on the other side, because the dielectric constant is linked to amount of water inside the concrete, so which changes during the hydration process. So that's allowed to trap the amount of water consumption during the concrete curing process. That is linked then to the degree of hydration. Degree of hydration is commonly used for estimating the strength of concrete at a different hydration stage. Some interesting observation is for hydrating concrete, a big portion of water actually is not consumed by chemical reaction, but reside inside the concrete that's available for maybe reduce the moisture shrinkage. It is an issue. And then from the electric conductivity, we then can found that there's a link of electric conductivity to the strength of concrete. And then we come up with this empirical estimation that's allow if we are able to predict the development of the electric conductivity, and then we estimate the strength of concrete. So this is some of the validation results. The other domain is like because for construction, for what's called freezing damage in concrete, particularly in the early stage. So in the construction in the cold region, because there's some strict specification requirements for these kind of activities. So essentially, like the construction season for concrete construction is limited by the weather condition, particularly in the cold climate. Like when the temperature, for example, DOTs like Ohio DOT, if the daily average temperature is below freezing temperature, then there's a mandate, for example, like 5 days thermal curing, which involves a lot of cost in particular for large project to maintain the temperature above zero. So like the decision process for 5 days thermal curing is an empirical maybe like a policy. So we look into how do we use instruments to provide input decision about like construction decisions. So this is based on because to prevent freezing damage to happening, for example, for concrete, what the physical criteria requires is we need to, because when water freezing into ice, there's a 10% volume expansion. So we need to make sure that there's a sufficient amount of open air voids inside concrete that are able to accommodate 10% volume expansion by the free water when they freeze into ice. The other thing is in the case if the ice crystal develop inside the concrete matrix, the concrete matrix needs to have sufficient strength to resist the internal pressure produced by the ice crystal. So these are the two mechanism criteria to mitigate freezing damages. So in terms of this one, because with the time domain reflectometry, what it can measure is the demand free water, and based on the phase diagram analysis, actually you can estimate the amount of air void inside the concrete. So essentially, with instrumentation monitoring in fresh concrete, what we can determine is how the water content, how the air void will change over time during the curing process. Then this one then allow to institute like a volume expansion criteria to prevent to judge if the freezing damage will happen inside the concrete. So these are for two different types of concrete material. One is without air entry admixture, so which means there's a less amount of air bubble inside the concrete during the mixing process. So with TDR, we're able to monitor the amount of water which is decreasing over time, and then the amount of air void which is increasing over time. So essentially, the intercept will tell the time corresponding to the intercept will tell at which time like the amount of air void inside the concrete is sufficient to accommodate the 10% volume expansion. That's allowed to make it more like a data-based decision for the concrete curing process. So now, for example, in construction Ohio, we don't have to wait for 5 days as a mandate. Maybe some concrete maybe only needs 2 days for thermal curing. That will significantly save the cost of construction. For the other case, for concrete mixture that's very well designed with a lot of air entrant admixture, it has much larger air content concentration that then there's less amount of issue with internal damage because of freezing. So with this TDR principle, we then introduce like instruments to assist cold region constructing decisions. Another domain I'm trying to briefly go over is what called spring load restrictions. So this is a common like a pavement preservation strategy in a lot of cold region state. I think that this practice primarily, I think maybe most people are familiar, is during the spring season when the ice under the pavements melt, the ground becomes soft. There's about like 20 states and Canada and northern European countries had what called spring load restrictions. During that period, like there's restrictions about the magnitude of the truck load that can run on highway. This serves as a pavement preservation strategy. So mining like like state institutes this spring load restriction in a very empirical way, and then not as much mostly by by law, but then less of by technology support. So if we say like if we can have a technology to monitor the ground freezing condition, that will then help us to improve the decision process. So in terms of monitoring principle, we say like when the water transition into ice or ice transition into water, then there's some unique change in terms of physical behaviors. For example, because it's a crystal material, when the water melt or freeze during the phase transition, the temperature typically maintained as a constant in a bulk-free water condition. So like, which means by monitoring the temperature, ground temperature, we can potentially have a way to monitor the ground freezing condition. And then like when water freezing into the phase transition, freeze or thaw, they change the electrical conductivity of soil as well. So that potentially has another way for monitoring the ground freezing condition. And then similarly, for the water transition, they change what's called a dielectric constant, because the amount of free water is decreased. For example, when water freezes into ice, that will cause changing the electrical properties, dielectric constant. So this is just the three maybe common sensing principles that allow to monitor the ground, extend the ground freezing. And there's also other like ways, for example, using fluorescence tube, which include fluorescence material with a transition, like the color would change at a transition temperature of 0 degree. So the instrument will involve like drill a hole into the ground, put the fluorescence tube into the hole, and then from time to time pick up this fluorescence tube to observe like the transition of the color inside of the tube demonstrated by the dye. And then this is the manual measurement in most in the practice. So essentially, in terms of dielectric, like electromagnetic response (TDR), the basic principle is like when for water which has a large dielectric constant, when it's transition to ice, there's a big transition in the dielectric constant. The ice is a solid, so it has much smaller dielectric constant, which means overall response by the electrical signal is very sensitive to the water-ice transition. So if we like in a trial process, we actually did a comparison of 3 different sensing principles to say which one has the best potential to monitor the ground freezing condition. So in terms of TDR, for example, when like these are the like a regular soil sample, if we freeze the soil at a different extent of freezing, the dielectric constant decrease because of the transition of water into ice, which demonstrates much significant decrease of dielectric constant. So with this in mind, then we then did a comparison about 3 different sensing principles for in terms of the ground freezing monitoring. So for example, for TDR, time domain reflectometry, it monitors the amount of liquid water inside soil. So it's way like for the transitions, the dielectric constant is indicative the amount of liquid water in soil. So during the freezing process, and for example, when the temperature initially decreased to the around 0 degree freezing temperature, glass like 0 degree, like dielectric constant maintain approximately stable. During the freezing process, dielectric constant decrease. When all the water, most of the water freeze, they become stabilized. Well, if we look at the electric conductivity, like electric conductivity continue to decrease with decreasing temperature, but we cannot see a clear transition at 0 degree. So for example, maybe just 20 degree to 0 degree still decrease. When the decrease into like a set ice formation still continue. So which means technologies that's based on electric conductivity will not be able to tell like when the freezing or thawing started, like begins. And then similarly for the like a temperature measurement, if we use a temperature to monitor freezing, thawing, the things is like the temperature remain approximately stabilized in certain fashion. So essentially that's like if we have a temperature data, it does not tell what the extent of freezing, thawing happening inside the soil. That's a general observation. But then compared with that, like dielectric constant by TDR, well, it's able to tell the extent of freezing. So what's percentage, what's on-site and what's percentage of freezing thawing. So that's the unique advantage. So with this, so the sensing probe, so we developed these customized sensing tubes that's allowed us to allow the testing to be done in a non-destructive way. We soak the soil sample, for example, we have that duplicate soil sample, soak the soil sample into the TDR tube, and monitor the freezing thawing process. And then we have duplicate the soil sample that allow to test the soil mechanical behavior destructively at a different extent of freezing and thawing condition. With this, then we can obtain a lot more detailed information about the behaviors of frozen soil or a behavior of frozen ground, if we extend that one. In terms of, like, for example, signal response, electrical signal response, the more like mechanical behaviors of soil, during the freezing and thawing process, with the accurate knowledge about the extent of freezing, extent of thawing. So that's the advantage. Would allow to institute more data, sensor data based mechanical analysis about freezing thawing ground conditions. And then for the application domain, we collaborated with Minnesota DOT to evaluate the performance under the realistic field application conditions. As described, spring load restriction is widely used in a lot of states and also European countries, Canada. What has been found is if restrict the load, like a traffic load, the truck load in the spring season when the ground melt, there's a major benefits in terms of life extension of pavement surface life. But then they have a disruption for the transportation free network, like dairies, wood. So they have an impact on the other transportation industry. So like properly decided, the level of duration of spring load restriction have a lot of implications for both payment durability and also for some other industry that use the road as for their service. From technology wise, like a lot of countries use technology, like different type of technologies, like frost depth management, falling wave deflectometer. In the United States, most states set a fixed time. So regardless of climate condition, the state's code just mostly institute a fixed duration. Definitely there's a room for this kind of improvement. So we worked with Minnesota DOT, develop a TDR sensor like this. It's a belt-shaped sensor, which allow to have a small drilling hole to install to monitor the frozen depths along the probe. And then this is a conventional TDR sensor. The TDR is also used in the pavement industry for monitoring underground water condition. So this is the conventional TDR we actually did on Ohio DOT construction site. I think this site involved install like a 12 TDR sensor at a 6-inch interval to monitor moisture distribution along certain range under the ground. With a conventional TDR probe, then we have a big borehole, put the probe and a lot of cable to manage. We developed this new sensor. It's a distributive moisture sensor, which allows to monitor the distribution moisture along the probe. Then we actually can use much smaller hole to install this one, and we only need one cable to get a signal out, compared with the 12 cables. To illustrate the performance, it's like if it's a flat TDR probe versus the TDR probe we artificially put a wet spot, emulates moisture variation. So this is the TDR signal response for a flat TDR probe. And then if we have moisture spot along the probe, then we have distinctive response from TDR signal. From the color, we can see this one has higher moisture, and this is a glass filled with water. So we see the extent of response is very related to the amount of moisture condition as well. So this is just a demonstration of the distributive sensing capability. So we can use a single probe to sense the moisture distribution along the probe without the need to put 12 cables, manage 12 sensor probes. So that's a major advance we made. So we work with Minnesota DOT on main road to install this sensor to monitor the performance. Actually, like from the response aspect, we found very encouraging data from the field demonstration study. Actually, what we found is using the freezing index, which is monitored by main road, versus the TDR monitored by the temperature measurement, versus TDR monitor freezing thawing process. What we found is they have a very consistent relationship. And then we actually was also to be, was able to monitor the freezing process. For example, underground freeze, we see like a change, like because reduction in liquid water. And then during the thawing process, we see a systematic change in the signal response. And more detailed analysis would then unveil what the moisture distribution happens under the ground. So that then provide a way to use the instrument to pilot data that allow to make some spring load decisions about spring load restrictions. And then for the other domain, we explore, essentially for example, Bridge Scour. The Bridge Scour is #1 cause of bridge failures. When we have a bridge foundation in the river channel, they cause turbulence flow, and then the erosion of sediment might cause the bridge to become unstable. Essentially, that's a challenging issue to resolve because a lot of what's called Scour critical bridges across the nation. And also Scour is the #1 cause of bridge failures in the United States, maybe in the other countries as well. So there's a lot of incidents, and so from instruments wise, there's a lot of different sensing approach people use to monitor extent of Scour. The conventional way is like a manual measurement. I said this is a photo shared by a Japanese research team. We did try to evaluate Scour condition. So there's also the other technologies serve this purpose. The most common one is use ultrasonics. So you have an ultrasonic transducer located along the bridge foundation to send out echo sound and bounce back, and then you detect the elevation of the riverbed essentially. And then there's other technology based on metal detector. So you drill install a tube, hollow tube into the ground adjacent to bridge foundation, and then you put a horseshoe metal circulate the tube, and when there's a erosion, soil will be taken away, the horseshoe metal will fall down, and then we then use a metal detector detect location of the horseshoe metal. That then allow to determine how deep the maximum depth the Scour has happened in the field condition. And then recently, there's people looking at structural response by fiber optic sensor, and using structural response like a vibration, like natural frequency of the superstructure as a way to detect erosion. And also people come up with what smart rock, which is which house a magnet, a permanent magnet, and then use a magnetometer to locate the location of the magnet. So instead, this smart rock would throw into the adjacent bridge foundation, and with the hole, it always falls to the deepest location when the Scour hole happens, evolves. And then they then use a magnetometer to locate where the magnet is located, and then find out the depth of Scour. And then pioneered by Dr. Dalton from Northwestern, they looked into TDR principle for Scour detection. It's very similar to the landslide monitoring concept. So you use a TDR probe, install adjacent bridge foundation, and then use a blade, crossing blade, to increase the water, to catch the water flow. Essentially, what happens if there's this erosion? This blade will be exposed to flow and then start to rotate, which then generates a torque on the probe, on the TDR waveguide, to cause a structural interface. And then this TDR sensor will then detect the interface, sequentially tell how deep the Scour happens. And then similarly for Army Corps of Engineers also looked into this kind of sensing principle using TDR. to detect the depth scour into the sediment. They were dealing with a more challenging situation because they study the ice rivers. So essentially, they then has to use a much stronger TDR probe to survive the ice, like scouring by ice during the freezing season. So we looked into this sensing concept that's using flexible like TDR belt. Like essentially, the basic concept is pretty simple actually. Launch a signal and then at the interface generate reflection and generate reflection. Our hope would be to based on this kind of sequential response, come up with an easy algorithm to come up to allow determine the depth of the interface between soil and sediment. So this is a prototype we come up with from the design, and then because signal look like simple, but then signal analysis to automate signal analysis is very critical for the long-term deployment. So we look into like using Siri as a guide, come up with an algorithm to analyze the signal in an automatic fashion. Actually, come up with a very simple way to interpret the signal that link the TDR measurement case dielectric constant measured to scour depth in a very simplified way by using the dielectric mixing relationship. And then we validate that one in the laboratory condition, and then on a different we also we also did a comparison with the alternative technologies. For example, ultrasound. This is also in the laboratory condition. So ultrasonic sensor, TDR sensor, and then when we change the interface between soil and the sediment, the TDR signal have a very systematic response. And then similar for ultrasound, they also have systematic response. The further away to the interface will have longer delay and then shorter and then more response. And then if we put them together, actually they have a comparable performance in terms of, because these are laboratory studies for this case. So we have accurate depths of the scour or sediment interface. The result for ultrasound and TDR will be comparable. But then if we say like in the actual scour, like a flood, for example, there's a lot of sediment, a lot of air bubble inside of the water because of turbulence flow. And then we have a lot of air bubble in the water. So how would that one affect the performance of different alternative technologies? So we then emulate that one by using air bubble generator, generate different extent of air bubble, emulates the actual water during the flood actually contains a lot of sediment, a lot of air bubble. So for TDR, what we found is signal is not significantly affected by the air bubble. So they just show very clean behavior. But then for ultrasound, if we with no air bubble, the signal looks a little bit clean. With air bubble, small amount of air bubble, start to see something coming up. In the reality, you might misinterpret that one potentially as an interface with sediment soil. And then if we increase it further, air bubble, and then it can completely blur the ultrasonic measurement, making it difficult to determine which one is actual the interface. If we don't even know or directly know in advance where the interface is located, you may likely to see this one is the interface. And then because that means ultrasound transducer is very close to sediment, which means the sediment didn't get erosion, but in the reality it's much deeper than this case. So that's the maybe consistent to common observation by people, by engineers in the field during the flood event, a sonic based device. Typically they don't provide reliable measurement when there's during the flood event. And then this part maybe is more like a research aspects, because we are interested to understand liquefaction for hazard mitigation purpose. So what have been found in the recent earthquakes, particularly the one in New Zealand, the Christchurch earthquake, what has been found is liquefaction tends not to happen in a uniform liquefiable soil, but in an interface between liquefiable soil with another nice permeable layer. So that's no permeable layer then cause the water to accumulate to develop a water film. That's called avoid the redistribution. And then that process significantly accelerate the liquefaction process. But then right now, there's no technology that's able to capture how this avoided redistribution develops during the liquefaction process. So we looked into using TDR to be able to monitor the film, because TDR is good with monitor how we can determine the film, how the water film grow. That presents a new challenge for the technology, because the TDR is every technology have a limitation. For TDR, the limitation would be how do we come up with the sufficient resolution to be able to detect the interface along the different soil layer. So we come up with this what's called spiral-shaped TDR sensor design. We use 3D printing to prepare this the sensor mounting system, and then we like tried in this earthquake shaking condition, and was able to monitor the water film. We have a physical measurement from the video analysis, and then from TDR signal response, we actually can find the results very comparable to the direct physical measurement. So this provides a way to use a sensor technology to monitor the liquefaction process as a way to understand the liquefaction mechanism. Okay, the other one, I mean, there's a lot of evaluation we have done over the past. So another one we were interested in looking to because the wind turbine, for example, wind energy, particularly in the cold region. One major issue is there may be ice form on the turbine blade that in the extreme case might make the blade to be unbalanced, and that could potentially cause into a dangerous situation. So we look, because TDR is good in monitor moisture and moisture ice transition. So we look into using electromagnetic wave like TDR to monitor the ice process to detect the ice on the wind turbine blade. But then this presents new challenges, similar to we have to use 3D printing for the spiral-shaped TDR. For this one, this case, the wind turbine blade mostly are made with polymers. So, but regular TDR is made with waveguide is by metal. So we look into like a conductive polymer as a waveguide that then allows to have a better compatibility with the wind turbine blade, and with the 3D printed model turbine blade as a test for validation, and then artificially introduced water and freezing process. Actually, from what we found is like the TDR signal response clearly indicates the development of ice on the blade. So that gave us the potential to mitigate the issue with like a wind energy safety issue in the cold region cold climate conditions. Okay, so run through a lot of different applications because time constraint. I cannot go into a lot of technical details, but then as a summary, like I call it as a TDR as one of the platform technology, because it is a sensing principle that's relevant to a lot of civil infrastructure purpose. So it's we explore a lot of like applications into soil, into concrete, into infrastructure, and then this benefited from some innovative concepts in the sensor design, new technology for sensor fabrication, like 3D printing, like electroconductive probe, conductive polymer probe, and then also benefit from signal analysis, because for long-term monitoring, signal analysis can be a critical issue. And then potentially there's like a lot of emerging, like people talk about Internet of Things for highway. So essentially there's a lot of potential to integrate, like embrace emerging technologies such as IoT, cloud computing, big data into the infrastructure sensing technologies, including TDR. That's maybe uncover a lot of new potential opportunities. Okay, so that's my presentation for today. Thank you for listening.
All right, thank you, Dr. Yu. We do have a couple questions for you.
Okay.
One of them is, how are the concrete parameters measured by TDR affected by the use of chemical admixtures, specifically liquid?
Yeah, that's a very good point. So based on our experience, because again we tried some limited recipes of concrete. So what we found is like the ionic concentration. For example, you say like sometimes I don't know, like for the, I assume you mean like the additives. For example, water reducer, different chemicals. Based on our experience, like this typically does not directly affect much the TDR measurement, but then they have an influence on because for each concrete, actually we did the customized calibration process. So essentially, the design recipe has an influence about the calibration. Like I think for the equation A and B I show, maybe I can. So maybe from the basic theory aspect, yeah. So for example, this one dielectric constant links the water and the amount of water, and then some design recipe, like A and B, for example, is a material dependent parameter. For soil, it's decided by type of soil. For concrete, that's a little bit dependent upon the mineral, like material, the mineral of the material inside concrete. So we account for that factor by doing a calibration first.
Okay, we have another question for you. For concrete application, if water content and temperature change and shrinkage develop simultaneously, is that possible to tell which factor affect the received signal or decoupling the different influential factors?
Yeah, that's an interesting question. Because like a TDR, what is measured essentially because the sensing principle, it mostly sense because of the change in the water. Because water change to the from free water to chemical bonded water. There's a big reduction in dielectric constant. Similarly, there's a big change in the structure-wise, change in the electrical conductivity. So a regular TDR measurement would be sensitive to the chemical hydration. That will be linked to the drying shrinkage, for example. It will not be able to differentiate if that's water change, it's because of chemical hydration, or if that's because of evaporation. So what it gives is the total amount of liquid water that has been consumed. The other aspect, like you mentioned, the shrinkage. I think that because typically the magnitude is so small, because TDR, like regular TDR sensor probe will not have the resolution to detect this kind of small physical change for example, in a volume reduction.
Okay, thank you. For the bridge scouring, how would you install the cable around the pier? If you attach the cable longitudinal along the pier, the scour hole may be on the other side of the pier.
Yeah, that's a good question. Because for TDR, because the sensor probe is what's called a fixed sensor, so which means it can only monitor the location that it was pre-installed. Yeah, that maybe is one limitation, because you can only monitor, each sensor probe can monitor only one location. If that's needed to monitor the scour at a several different location, then that one requires several TDR probes. But the installation procedure is very similar to the like this one. Actually, why? Because like this belt-shaped TDR sensor can be just installed like in a very small hole. So actually, we worked with Ohio DOT in a project that we did a demonstration to one of the outdoor like a highway bridge. What we did was we worked with a site investigation company, because they are commonly involved to sample the soil samples when they design new bridge for outdoors, for example. So instead, what we did was we directed coring through the concrete slab, like a cord through the bridge deck all the way through into the river channel, similar to what they typically do when they do site investigation to find the design parameters. And then we just use the common like site investigation procedure to put it, because essentially for sampling the soil, run the SPT test, they use a temporary PVC tube to support the soil structure, And then what we did was just install our tube, this TDR probe through the tube. And when the tube we withdraw from the river channel, the sensor is left in place.
Okay.
I don't have, I didn't put on like a photo to show that one because the time constraint for this. Yeah.
Oh, okay. Okay,
Yeah,
great.
I would be happy to show some. Yeah, okay. Yeah,
Yeah,
that's very interesting. Yeah.
I've told everyone if they have any further questions, they can email me, but we do have one more question for you, and we're a little bit over time, but that's okay. How do costs compare for TDR versus ultrasonic techniques?
For what purpose? You mean for Scour?
How do costs compare for TDR
Cost.
ultrasonic techniques?
So for example, I would say like the cost should be comparable. For example, the TDR like the TDR signal generator, I think is commercially available. It's like maybe around $20 to $2,400. And this TDR probe we customly designed. It's just like a metal strip. In terms of the material cost is very inexpensive. It's like maybe I don't know, maybe less than $10. But then there's some fabrication, there's customized fabrication there's some cost for that. The material cost for this one alone is not that expensive. Just maybe in terms of, I don't know, just this probe itself, like maybe in the range of $10 something, and this conversion head is something maybe $10, $20 something.
Okay. Excellent, thank you. There are no more questions in the queue right now, so I think we're done. If you do have any further questions, please go ahead and email me and I will forward them to Dr. Yu. And thank you everyone, and especially Dr. Yu, thank you for this presentation. It's very insightful. And stay safe everyone, have a great day.
Thank you, thanks Shira, thanks everyone. Have a great day, continue to stay well.
Okay, bye now.
Bye.